The question is proved by induction. X to the power of n minus y to the power of n is divisible by x minus y, where n is an even positive integer. Okay. So till now we have been dealing only with integers, right? Natural numbers, in fact. Okay. Positive integers, natural numbers. But in this question, if you see, they have said n is an even positive integer. Now, this is a problematic statement because till now we know that induction is only for statements with dealing with natural numbers. Okay, so this even positive integer we will convert to any positive integer. Okay, let's see how. We start by saying let Pn x to the power of n minus y to the power of n is divisible by x minus y, where n is an even positive integer or an even natural number. Now, as I said, that this even natural number, even positive integer is a problem. So we'll just modify the statement a little to include all natural numbers. How do we do that? We write this as, this can also be written as x to the power of 2k, because any even number can be written as x to the power n is equal to 2k, right? Minus y to the power of 2k is divisible by x minus y, where k is a positive integer. Now our statement will conform to the definition of mathematical induction, right? So you see the difference, even positive integer here, and k is any positive integer, that is a natural number, right? So now we can start this. For k is equal to 1, you have x to the power of 2 into 1 minus y to the power of 2 into 1 is equal to x square minus y square, which can be written as x plus y into x minus y, right? Which is divisible by x minus y because it contains x minus y as a factor. Right? So thus, let me write this as pk, because this is pn, we write this as pk. Okay, so thus pk is true for k is equal to 1, that is p1 is true, right? We'll now assume the statement pk. So let us now assume pk pm. Okay, let us now assume pm. What is pm? X to the power of 2m minus y to the power of 2m is divisible by x minus y, where m is a positive integer. And in brackets, we can write this as m belongs to n, right? We shall now show that pm plus 1 and what is the statement for pm plus 1? X to the power of m plus 1 plus x to the power of twice m plus 1, right? Replace m by m plus 1 minus y to the power of twice m plus 1 is divisible by x minus y, where m is a positive integer. M belongs to n is true whenever Pm is assumed to be true. Okay, so now the question is, how do we show this? So we start with x to the power of 2 twice m plus 1 minus y to the power of twice m plus 1. So we have x to the power of twice m plus 1 minus y to the power of twice m plus 1. Okay, this can be written as x to the power of 2m plus 2 minus y to the power of 2m plus 2, right? Which can be written as x to the power of 2m into x square minus y to the power of 2m into y square. Okay. Now see, because Pm I have assumed x to the power of m minus y to the power of 2m is divisible. Okay, so what we try to do here is we write x to the power of 2m, and instead of this x square, we write this as x square minus y square, right? And because we have, instead of this x square, I'm writing x square minus y square. So what is the extra that I have provided here? I've provided y square extra here. So I write add y square, right? And the second one I write as it is, y to the power of 2m into y square. Okay. Now x to the power of 2m, if I now separate x to the power of 2m into x square minus y square, that is, I'm multiplying this with this, plus x to the power of 2m into y square minus y to the power of 2m into y square, right? Which is equal to x to the power of 2m into, now this, if you see, x to the power of 2m, because p1 we have already checked, it is true. That means x to the power of 2m into, this is a multiple of x minus y, right? Right. And this one, what about the second and the third term? I can take y square out and write this as x to the power of 2m minus y to the power of 2m, right? So I have x to the power of 2m into a multiple of x minus y plus, and because we have assumed Pm to be true, x to the power of 2m minus y to the power of 2m, we have assumed this to be a multiple of x minus y. And the sum of the two multiples of x minus y must be a multiple of x minus y. That means x to the power of 2m, what can we say? If this is a multiple of x minus y, therefore x to the power of twice m plus 1 minus y to the power of twice m plus 1 is divisible by x minus y, right? So this shows that Pm plus 1 is true whenever Pm is assumed to be true, right? That is P, hence by induction we can say, hence by the principle of mathematical induction, Pk is true for every k belongs to n. That is, Pn is true for every even positive integer n. Okay, so this completes the proof. Any question?
No, sir.
Okay, next question. We have finished all questions on divisibility, right? The next question will deal with inequalities, how to prove mathematical inequality statements with the help of principle of mathematical induction. Okay, so let's see how to prove inequalities. New type of mathematical statement. Okay, first question is proved by induction 2n plus 7 less than n plus 3 for all natural numbers. So I say let Pn 2n plus 7 less than n plus 3 whole square for all n belongs to n, right? This is the given statement which we need to prove. Be the given mathematical statement. For n is equal to 1. What is the left hand side of the inequality? 2 into 1 plus 7, which is equal to 9. And what is the right hand side of the inequality? 1 plus 3 square, which is equal to 16, right? So clearly, left hand side is less than the right hand side, right?
Yes, sir.
For n is equal to 1. That is, P1 is true. Okay, so first postulate satisfied. Let's now assume the statement for Pm. So let us now assume Pm. What is the statement? 2m plus 7 whole square is less than m plus 3 whole square for all m belongs to n, right? We shall now show.
Sir, there will, sir,
Yes,
sir, there will be no whole square and 2m plus 7.
yes, this is a mistake. So we shall now show that Pm plus 1, replace m by m plus 1, so twice m plus 1 plus 7 less than m plus 1 plus 3 whole square for all m belongs to n, right? So assuming Pm, we are going to show Pm plus 1. So we start with Pm. So we have 2m plus 7 is less than m plus 3 whole square. Now if you see on the for Pm plus 1, what is on the left hand side of Pm plus 1? We have 2m plus 2 plus 7, isn't it? So what we are going to do is we are going to add 2 here. So 2m plus 7 plus 2. We are going to add a positive number. So inequality sign will remain the same. Okay. Why did we add 2? So that it comes to this form, right? Pm plus 1. So now what we have here? 2m plus 2 plus 7. And here what do we have? If you expand this, m square plus 6m plus 9. This is the expansion of m plus 3 whole square. and you have a plus 2, right? So what are we getting here? 2m. You can take 2 common here. Twice m plus 1 plus 7. So now see, have we got this here? Yes, left hand side is got.
Yes, sir.
Only thing is we have to show that this is less than the right hand side. So let's see what right hand side we are getting here. M square plus 6m plus 11 we are getting, right? But what do we have to show? We have to show it is less than m plus 4 whole square, right? Now we see that m square plus 6m plus 11 must always be less than m square plus because we have m plus 4, m square plus 6m plus 16, isn't it? Why did we write m square plus 6m plus 16? Because we see that this is nothing but m plus 4 whole square, isn't it? Right? And what is the expansion of m plus 4 whole square? It is m square plus 6m plus 16. We are getting what? M square plus 6m plus 11. And m square plus 6m plus 11 must always be less than m square plus 6m plus 16. Why should it be? Because m square plus 6m, this part is same for both, right? Only it differs in this part, isn't it? Here we have 11, here we have 16. And because 11 is less than 16, therefore the entire expression must be less than m square plus 6m plus 11 must be less than m square plus 6m plus 16. This is positive. So positive plus positive, positive plus positive, right? Clear? Why I wrote this?
Yes, sir.
Okay. So therefore, now if we combine the two, therefore what do we get? Twice m plus 1 plus 7 must be less than m square plus 6m plus 11, which is less than m square plus 6m plus 16, isn't it? That means now we can write this as twice m plus 1 plus 7 is simply less than m square plus 6m plus 16, right? That means we can write this as twice m plus 1 plus 7 less than m plus 4 whole square, right? Twice m plus 1 plus 7 is less than, now we can write this as m plus 1 plus 3 whole square, right? So have we got pm plus 1? Have we got
Yes,
this?
sir.
Yes. So this shows that pm plus 1 is true whenever pm is assumed to be true for every natural number m. Hence, by the principle of mathematical induction, Pn is true for every natural number n, right? So this is how we prove inequalities. Okay, any question on any step?
No, sir.
We finish the last problem. Part 2. Again, a question on inequality. Proof by induction, the statement. So let Pn 1 square plus 2 square plus 3 square up till n square is greater than n cube by 3 be the given mathematical statement where n is a natural number. For n is equal to 1. What is the left hand side? Only 1 square, which is 1. And what is the right hand side? 1 cube by 3, which is 1/3. So clearly, left hand side is greater than the right hand side. So therefore, P1 is true, right? Or we can say Pn is true for n is equal to 1. Okay, so P1 is true. Let us now assume Pm 1 square plus 2 square plus 3 square up till m square is greater than m cube by 3 for every m belongs to n. We shall now show that Pm plus 1. What is Pm plus 1 statement? 1 square, 2 square, 3 square up till m square, and you have an extra term. M plus 1 whole square is greater than, replace m by m plus 1 on the right hand side. So m plus 1 cube by 3 for every m belongs to n is true whenever Pm is assumed to be true. Right? So we start with Pm. So we have 1 square, 2 square, 3 square till m square greater than m cube by 3. Now we want to bring it to Pm plus 1. So what is the extra term in Pm plus 1? M plus 1 whole square. So we add m plus 1 whole square to both sides. Adding m plus 1 whole square to both sides. And inequality sign will not reverse because m is a natural number. So m plus 1 whole square definitely will be positive. We get 1 square plus 2 square plus 3 square up till m square plus m plus 1 square is greater than m cube by 3 plus m plus 1 whole square, right? Now see, we have already got the left hand side of Pm plus 1. Only thing is we need to show this, that is this quantity is either equal to or less than m plus 1 whole cube by 3. So let's start with this. What is this quantity equal to? If you take the LCM here, you get m cube plus thrice m plus 1 square, right? Which is equal to m cube plus, if you expand this, you get 3m square plus 6m plus 3 divided by 3, right? Get m cube. Now see, this is, and this cannot be simplified any further, right? So we are getting m cube plus 3m square plus 6m plus 3. And in Pm plus 1, what is the statement here? On the left, on the right hand side, m plus 1 cube by 3. So this quantity that you see here must be greater than m cube plus m cube plus 1 plus 3m square plus 6m by 3. Because see, all the terms are same here. We have m cube here, m cube here. We have 3m square here, we have 3m square here. We have 6m here, we have 6m here. Only thing is this 3 is greater than 1. So that is why this entire expression must be greater than this, right? Clear with this step? This step is critical. Tell me.
No, sir. No,
Yes?
sir. No,
Not
sir. I did not understand.
not clear. Okay, okay. Fine. So we reached till this part. Till this part is okay. So what have we got here? So therefore 1 square plus 2 square plus 3 square plus up till m square plus m plus 1 square. We have got this is greater than m cube plus 3m square plus 6m plus 3 divided by 3, right? This is what have we got till now.
Yes, sir.
So we see that this quantity m cube plus 3m square plus 6m plus 3 divided by 3 must be greater than m cube plus 3m square plus 6m plus 1 by 3. Can we write this? That this quantity is greater than this,
Yes, sir.
right? Only because this 3 here is greater than this 1 here, isn't it?
1.
Right. So if this quantity is greater than this and this one is greater than this, then what can we write? 1 square plus 2 square plus 3 square m square plus m plus 1 square must be greater than this one. Can we write this?
Yes, sir.
Now the question is, the obvious question is that why should I make this quantity greater than this quantity? Why was there a 3 and why did I write this as 1 and why did I give a greater than sign here? Why only 1? I could have given a 2 also, isn't it? Why have I given a 1 here? Because if you see pm plus 1 contains what? M plus 1 whole cube here, isn't it? And if you expand m plus 1
Yes.
whole cube, you will get m cube plus 3m square plus 6m plus 1. Understood?
Yes, sir. Yes, sir.
So that means I can write this as greater than m plus 1 whole cube divided by 3. So we have proved pm plus 1. So this shows
Yes, sir.
that pm plus 1 is true whenever pm is assumed to be true. Hence, by the principle of mathematical induction, Pn is true for every natural number n. That's it. And that is the end of your syllabus.